Hello students, today we're going to cover section 6.8, Applying Coordinate Geometry. By the end of this lesson, we'll be able to name coordinates of special figures using their properties. The first thing that we need to discuss is the importance of picking the correct variables. If we think back to chapter 5, we learned triangle midsegment theorem. Below, we'll take a look at three potential locations to place a triangle in the coordinate plane such that we can prove the triangle midsegment theorem. The first location of this figure has coordinates for P, Q, and R, and all of the coordinates are variable locations. So we have vertice P at coordinates A, B. We have the coordinates of Q at C, D. And finally we have the coordinates of R at E, B. You'll notice here that the y coordinate of both P and R are exactly the same. In other words, P has moved some distance right and then up some distance B, where R has moved right some distance E and then up that same distance B. That gives us the base of this triangle, which is horizontal or parallel to the x-axis. If we wanted to do anything with the triangle midsegment theorem, we might need to find the locations of both M and N. So here we need to find the locations of the midpoints. So for M we have the average of A and C for the x coordinate, and we have the average of B and D for the y coordinate. For the location of N, we have the average of C and E for the x coordinate, and we have the average of B and D for the y coordinate. However, if we take that triangle and slide it into a slightly different location, so here we've taken the base and we've slid it so that one of the vertices is at the origin, and we've forced the base to be on the x-axis. We can see that it changes the coordinates in such a way that we have no variables for P, right, because P is now at the origin at 0, 0. Since R is now on the x-axis, it has no y coordinate, but it has an x coordinate. And we have Q, which is now at A, B. So now rather than having 5 variables, we only have 3, A, B, and C. If we again found the midpoints M and N, we'll find in this case that the x coordinate at M is the average of 0 and A. So this is now just A over 2 for figure 2. And the y coordinate is 0 plus B over 2, or just B over 2. So we've considerably simplified the coordinates of M. The coordinates of N in this case, we take A plus C, or the average of the x coordinates, and we take B over 2, the average of the y coordinates. So you can see in this case that the movement from figure 1 to figure 2 has simplified the coordinates quite a bit. Let's take a look at one more location. So here you can see that the triangle has been slid a little bit to the left. The base of the triangle still falls on the x-axis, but the third vertice now belongs on the y-axis. In addition to that, the x-coordinate at P has now become negative. There are also coefficients of 2 applied to some of the variables. And so let's see what happens to the midpoints. In this case, if we're looking for the midpoint of M, we take negative 2a plus 0 and divide that by 2. And for the y coordinate, we take 0 plus 2b, or 2b, and divide by 2. And for the coordinates of N, we take 0 plus 2c and divide by 2. And we take 0 plus 2b and divide by 2. So in this case, because of the 2's, all of the 2's cancel each other out. So in this case, we get negative a, b, and over here for the coordinates of N, we get c, b. So if we take a look at all of the potential figure locations for this triangle, we can see that the final location ends up being the most simple with the variable coordinates. this choice of location would be the best to complete a coordinate proof. So let's look at a problem where we're asked to name the coordinates of the vertices of the figure. So here we have RECT, which is a rectangle. It has a height of A and a length of 2B. So let's start by marking that on our diagram. So we have a height of A and a length of 2B. It also says that the y-axis bisects segment EC and segment RT. So in this case, the y-axis cuts EC and RT exactly into two equal parts. So we're asked to give coordinates of the four vertices of this rectangle. So thinking back to what we know, all the points that exist on the x-axis have a y-coordinate of 0. So in this case, that would probably be one of the best locations to start. We also know that coordinates to the left of the y-axis have negative x-coordinates. So we can apply those negatives. Now, if we're going to go some distance to the left and then up, we can see over here that we were going up a length of A. So in this case, we go some distance to the left and we have to go up A, so this is going to get A. And here we go right some distance and then up A, so we can see that the y-coordinate here is A. So now we've taken care of the height of A, and you can see we have all of the y-coordinates. So if this is the total distance of 2b, then splitting it in half will give us two parts of b. So we can see this is b to the left, and this is b to the right. So we can see this will be negative b comma 0. This will be negative b comma a. Here we go to the right b and go up or down 0. To get to C, we start at the origin, we go to the right B, up A. So we can see that the coordinates of this rectangle would be given as negative B comma A, negative B comma 0, B comma A, and B comma 0. Another example of this type of problem is kite, K-I-T-E, where segment IE has a length of 2A, segment KO has a length of B, and segment OT has a length of C. In this case, the x-axis bisects segment IE. So we have two congruent segments. OI is congruent to OE. And since its entire length is 2 times some variable A, we can say that each part has a length of A. The distance from K to O is B. So this has length B, and the length from O to T is C. So if we want to label the coordinates of I, we go left or right 0. We go up A. To find the coordinates of T, we go left C. We go up 0. To find the coordinates of E, we go down A. So in this case, we go left or right 0, we go down A. And to find the coordinates of K, we go left B, so that's negative B, and we go up or down 0. So we now have the coordinates of K, I, T, and E. So given variable coordinates, we might be asked to prove something. So in this case, the diagram shows a trapezoid with a base centered at the origin. And the question is this trapezoid isosceles? And we're asked to explain. So we need to know what it means for a trapezoid to be isosceles. And if we think back, we have to show that the length from R to T is the same as the length from A to P. So in order to do that, we're going to need distance formula. So distance formula is the square root of the change in the x-coordinates squared plus the change in the y-coordinates squared. So to calculate the distance from R to T, we have R to T equals, and let's establish this is point number 1 and this is point number 2. We want x1, so we have negative b. we want minus x2, so we want plus a, and we want to square that, and we want to add to that y1, which is c minus 0 squared. So let's go ahead and calculate the distance from A to P. If we assign this as 0.1 and this is 0.2 on this side, we have the square root of, in this case, x1 is b, minus x2, which is a, squared, plus we have y1, which is c minus 0 squared. So in this case, we can see that the two formulas look very similar. In fact, the only difference in the two formulas is this section right here. We have negative b plus a squared on one side, and we have b minus a squared on the other. So if we can show that those two things are the same, then the two formulas would have to be the same. So let's go ahead and do FOIL on those two sections. We have negative b plus a multiplied by itself, so negative b plus a. Remember, first times first, so we have negative b times negative b, which is just going to be b squared. Outer times outer, so negative b times positive a, so we have negative ab. Inner times inner, so we have positive a times negative b, which is negative ab. And last times last, so positive a times positive a, which will give us positive a squared. We have two common terms in the middle, so here we have b squared minus 2ab plus a squared. So let's FOIL the other side and see if we end up with the same thing. So we have b minus a times b minus a. First times first, b times b is b squared. We have b times negative a, so we have negative ab. On the inside, we have negative a times b, so negative ab. And last times last, negative a times negative a is going to give us positive a squared. Again, we have the common terms in the middle, so we have b squared minus 2ab plus a squared. So now we can see that the two highlighted sections are actually the same thing, which means that the distance from R to T is the same as the distance from A to P, and therefore this trapezoid is isosceles. So oftentimes, things that are a little bit difficult to do as a two-column proof can be done as a coordinate proof. We just set up a figure in the coordinate plane and use algebraic methods to prove theorems. So there are 3 steps to a coordinate proof, which will be our primary focus of section 6.9. So the first step is to draw and label a figure. So if we wanted to plan a coordinate proof of the triangle midsegment theorem, which is theorem 5-1 in your book, we should first start with a triangle and its midsegment. So much like we saw at the beginning of the section, I've placed the triangle so that its base is along the x-axis and its third vertex is on the y-axis. This will help me so that I can make the proof as simple as possible. We'll get back to labeling the figure in a second, because I'll show you one of the things that makes labeling the figure a little bit easier in step 3. So the next thing that we're told to do in step 2 is to write the given and prove statements. So the given in this case is that we have some triangle ABC with a midsegment drawn. And so we'll label it DE. So in this case, it makes sense that we have ABC as our triangle, and the midsegment is DE. If we think back to triangle midsegment theorem, we need to prove 2 things. We need to prove that segment DE is parallel to segment AC in this case. And we also need to prove that DE equals half of AC. If we go with the coordinates from the beginning of the lesson, that is negative 2a comma 0 for A, 0 comma 2b for B, and 2c comma 0 for c, we can begin to discuss the formulas that we need to set up this proof. In this case, first, we need to find points D and E, so we're going to need midpoint formula. In addition to that, we need to show parallelism, so we're going to need slope formula. And we need to show that segment DE is half the length of segment AC, so we'll need distance formula. So here we have a drawn and labeled figure. We have the given and proved statements, and we've determined the formulas that will be needed to complete this coordinate proof. We will complete this coordinate proof in section 6.9, but until then, this is as far as we need to take this problem. That concludes section 6.8, applying coordinate geometry. We now know how to name coordinates of special figures using their properties.